Section 5.1, solving systems of linear equations by graphing. Alright, so what we're going to look at here in this chapter is something called systems of linear equations. Oftentimes it's called systems of equations. Systems of equations are when you have more than one equation at the same time, and you're looking for a solution that works for all equations. We're primarily going to be working with two equations, but you could do this for multiple equations beyond that. Let's look at this problem here. Mr. Callan and the math team are selling slices of pie for Pi Day, March 14th, as a fundraiser. They plan on selling the pie for $2 per slice. To place an order with the local bakery, they have to pay a flat rate of $12 to start the order, and then pay $1.50 per slice. How many slices of pie do the mathletes need to sell in order to break even at the end of the day? So, kind of looks a little complicated. What we can do is we can write two different equations based on the information that we have. We can have how much we're going to be spending and how much we're going to be making. Let's start first with the easier one, how much money we're going to make. Since we're going to be making $2 per slice, we're looking at a very simple equation. Y equals 2x. $2 per slice, that tells us that $2 is a slope. We have no y-intercept that we need to worry about, so we don't have a plus b, it would just be a plus 0, and that's our first equation. Our second equation comes from the fact that we're starting to pay this bakery $12, that's going to be our y-intercept, and then $1.50 per slice. Again, the per tells us that that's our slope. We get 1.50x plus 12. That's our y-intercept. So these two equations will tell us how much money we're taking in and how much we're spending. As long as these two end up being equal, we're in good shape. So one way we can see this is by graphing. Now, in order to graph the first equation, not a problem at all. To graph the second one, 1.5 is a little tricky, so I'm maybe going to be better off using a fraction. And I might recognize that 1.5 is the same thing as 3 over 2. That will allow me to use rise over run when I'm doing my slope. So what you would do is you'd graph those two equations, the y equals 2x and y equals 3/2 x plus 12. Graph those on the same coordinate grid and see what happens. Alright, so now if we look at the graph, I've used Desmos here to graph these two lines. You could graph them on your own coordinate grid paper or on graph paper or using something like Desmos or Calgebra. But I have my first line here, which is how much I'm making, y equals 2x, and the other line, y equals 3/2 x plus 12. You see these lines are getting closer to closer together, and eventually they actually intersect right here at the point 24, 28. Now, the 24 is an x value, and remember that x is the number of pies. Right? 48 is a y value, and that's actually a cost value. So you can see that if I sell 24 pies, 2 times 24 is 48. That means I'm going to be getting $48. But at 24 pies, I also have to pay for each of those 24 pies at $1.50 each, and that's $36, plus the $12 that I originally paid for setting up the order, and that's a total of $48. So I have to sell 24 pies, or the mathletes have to sell 24 pies in order to break even. Any more pies than that, and we're making money. Any fewer pies than that, and we've lost money. But that's what the graph tells us. Where these lines intersect is going to tell us exactly what our solution is. So this is what we call a system of equations, these two equations right here. And the solution is an ordered pair. In this case, that ordered pair is 24, 48. And that's all that it is. Graph the lines, see where they intersect. Well, okay, in all honesty, that's how easy it is, but there are actually three different possibilities that could happen when you graph the lines. It's possible that our lines are what we call inconsistent, or that it's an inconsistent system. That happens when we have parallel lines. These lines, which have the same slope and different y-intercepts, will never intersect, which means that there is no solution to the system. So if you graph lines that have the same slope and they're parallel, you would just say no solution. That's called an inconsistent system of equations. there are two different consistent equations. The first one is independent, and that's the example we just looked at. This is most typically what you're going to see. Two lines with different slopes, they're going to have one point of intersection. Two lines, if they're going to intersect at all, at one point, it's only going to be 1 point. You're not going to have it intersect at 2 different points. That's our typical answer. We're usually going to have one solution, and we're going to write it as an ordered pair. The other type of consistent system has solutions, but not just one. It may be tough to tell, but there are actually two lines here. This is what we call a dependent consistent system. These two lines actually have the exact same equation. Maybe it's y equals 2x plus 4 and y equals 2x plus 4. It's the exact same line, so they overlap everywhere. They intersect at all of these different points. They have an infinite number of solutions. This is not the same as all real numbers, but it's the same kind of idea. There's more than one answer. There's an infinite number of them. So these are the three possibilities. The one in the middle is the most common one we're going to deal with. But definitely inconsistent, which is no solution for parallel lines, or dependent, infinitely many solutions for the same line, will show up. But again, your focus is going to be on one solution, consistent, independent. In closing, I just want to point out one of the limitations of graphing. Here we have a system of equations, again using Desmos. The red line is y equals 2x plus 2. The blue line, y equals negative 3x plus 4. And we can see that these two lines do intersect. It's a consistent, independent system. But they intersect here. And what's a pain about that is that it's between 0 and 1 on the x-axis and between 2 and 3 on the y-axis. And based on our graph, we really can't get a better answer. We could estimate. Maybe it's about 2.3, 2.7 or something, or 0.3, 2.7. We're not really sure. We might approximate our answer. It's an approximately equal sign. 0.3, maybe 2.8. I'll call it something like that. I'm really not 100% sure of what it is. It's tough. We can't guarantee it. So this is one of the problems with graphing, is you can't always tell exactly what your answer is. We could get a rough idea, but we're going to learn soon some other methods to solve this that will be a little bit more exact, a little bit more algebraic. So that's our limitation, but it is still something that kind of works. All right, I hope that this makes a lot of sense.